Hello everyone, welcome to HYDROSTATIC.com. Today we are going to discuss the hydrostatic force on an inclined plane surface submerged in liquid. To discuss this, let us consider a plane surface of any shape which is inclined at an angle theta below the free liquid surface, and if its center of gravity is h bar below the free liquid surface, and the center of pressure due to the fluid that will be acting on it, dividing it into several strips of area dA with thickness dy, acting at a distance y from a line OO that cuts the free liquid surface. Let the center of gravity G be at y bar from OO, and y star be the distance from OO to the center of pressure. We begin with the small area on this surface. So if we are dealing with several strips, we have to also find the force on each small area. So if the small area has a force dF acting on it, this dF is equal to the pressure acting on it times the area, and that pressure P is equal to rho GH. Now substituting it in this expression, it means dF rho GH dA, meaning that for us to discuss this, we are going to find the total force, and it will be the sum of these forces acting on small strips of area, and this will equal to sum of rho GH dA, which is equal to the integral of rho GH dA. If we call that equation star, know from geometry, h over y is equal to h star over y star is equal to h bar over y bar is equal to sine theta. Then f will therefore equal to rho g integral of y sine theta dA. Now we know if it is equal to rho g sine theta integral y dA, this expression integral of y dA is the first moment of area about OO, and this gives you the sum of the moments of areas that compose that particular entire surface. And therefore from the principle of moments, we know that integral of y dA is equal to also the moment of the entire area from its centroid to the axis that has been chosen. So if the axis is OO, then it means will be A times y bar, and is equal to integral of y dA. So that means this force F will therefore equal to rho g sine theta times this expression here, A y bar, which is the moment of the entire area about a line OO cutting the free surface. Now let us call this equation A. So this is the hydrostatic force that acts on the body and acts at a distance y star from the line OO that cuts the free axis. Center of pressure y star about OO. It means we have to look for the moments of this force about OO, and we also get the moments of the several forces on the area strips about OO. So let us find the moment of dF on area strips. It means the moment of dF about OO will equal to dF times y, which is equal to, we know this is the same as rho g rho g h dA times y. But we already know that y is equal to actually it is h over y is equal to sine theta, meaning that now that h is equal to y sine theta. So we substitute it in here. This force dF times y will equal to rho g sine theta times y squared d. Now total moment will equal to sum of these moments of the several forces on the strips of areas, then it means it will be sum of rho g sine theta y squared dA, which is equal to rho g sine theta integral of y. Now this integral y squared dA is equal to I naught, which is the second moment of area about. So it means the sum of moments of these several forces, that is total moments, equal to rho g sine theta times I naught. Let us call this equation B. Now what about the moment of the hydrostatic force? The hydrostatic force F. This force acts at the center of pressure, and therefore its moment will be F times y star about OO, which is the distance of the center of pressure from line OO that cuts the free surface. And this will equal to, according to equation B, and from the principle of moments, F times y star will equal to rho g sine theta I naught. Now it means, from again equation A, from A, F is equal to rho g is equal to rho g, we know it, rho g sine theta is equal to rho g sine theta A y bar. So which means that rho g sine theta A y bar is equal to rho g sine theta I naught. This is times y star. So meaning that y star will equal to rho g sine theta I naught over rho g sine theta A y bar. This and that will go, so that I remain with I naught over A y bar. So the center of pressure is at the distance y star, which is equal to I naught over A y bar. But we know from principle of parallel axes, I naught can be obtained, and I naught will equal to Ig, which is the second moment of area about an axis passing through the centroid of the surface, plus area of the entire surface times the square of the distance between an axis taken and the centroid squared. That's what the principle of parallel axes mean. So it means here that y star will equal to Ig over Ay bar plus ay squared over ay bar. This and that will go, so that this whole expression will be ig over ay bar plus y. Therefore, the center of pressure will be at a distance y star, which is equal to ig over ay bar plus ig can be obtained. Because we know ig is known from geometry. For example, for a rectangle of these dimensions, if this is its center of gravity g, then it has a distance b here, then this is a, then ig is obtained from a b cubed over 12. For a rectangle, that is it. For a triangle, if this is a triangle and this is g, then this is g, this is h from there to there, and maybe this is a. Its ig, which is the second moment of area about an axis passing through the center of gravity, is equal to a b ah cubed out of 36. Now, if this y star is the center of pressure about an axis OO, then if it is required in terms of depth h, then from h star over y star is equal to sin theta. It means y star will therefore equal to h star over sin theta. So substituting it in this equation, if this equation is called equation C, from equation C, if we substitute in a value for y star, it means h star over sin theta is equal to ig over a times y bar. So it means also y bar is h bar over sin theta plus y bar, which is also equal to h bar over sin theta. So to make h star the subject of the formula gives you ig times this sin theta will move up, sin theta times sin theta, everything over a h bar plus h bar over sin theta times sin theta. So that and that will go h star, which is equal to ig sin squared theta out of a h bar plus h bar. So therefore, this is the distance of the center of pressure from the free surface axis. The hydrostatic force is equal to rho g sin theta a h bar.